When we think of the strongest materials in the universe, our minds usually go to diamond or graphene. The secret to their strength is proximity. In a diamond lattice, carbon atoms are packed incredibly close together, creating short, rigid, covalent bonds. The rule of thumb is simple. The closer the atoms are locked together, the harder it is to tear them apart. We measure this fight back with the Young's modulus. Steel is strong at 200 gigapascals. Diamond is the king of Earth, sitting at over 1,000 gigapascals. But even diamond hits a limit. If you zoom in on its lattice, you realize that close is relative. These atoms are still distinct islands, held apart by their electron clouds. Relative to their size, they are miles apart. But what if we deleted that space? What if we could push past the electron clouds and force the atomic nuclei themselves to touch? In this case, you wouldn't just get a harder diamond. You would trade the weak glue of chemical bonds for the infinite grip of the strong nuclear force. You would unlock a material stiffness that is physically impossible on Earth. But where in the universe exists a press powerful enough to do that? Where could such extreme conditions possibly exist? The answer lies in the most violent event in the cosmos, the death of a massive star. When a star goes supernova, gravity crushes the core with such violence that it does exactly what we predicted. It smashes the electrons inside the protons, creating a neutron star. This object is the universe's hydraulic press. Beneath its atmosphere, the star is stratified into layers of crushing pressure, getting denser the deeper you go. The density here is so enormous that a single sugar cube of this material weighs as much as Mount Everest. That is 100 trillion grams per cubic centimeter. Obviously, we can't visit and verify this. If you stood on the surface, gravity would flatten you into a puddle of neutrons instantly. So to see what this material actually looks like, scientists had to build it inside a supercomputer. Researchers use molecular dynamics simulations to recreate this hellscape inside a digital box. They simulate roughly 100,000 protons and neutrons, subjecting them to the same insane forces found inside the star. And the simulation reveals a war between two fundamental forces. First, you have the Coulomb force. Since protons are positively charged, they hate each other. They want to repel and fly apart. But fighting against them is the strong nuclear force, the glue that wants to bind them together. Caught in this tug of war, the matter enters a state of geometric frustration. The short-range strong force tries to bind the particles, while the long-range Coulomb force pushes them apart. To minimize energy, the system compromises, balancing nuclear surface tension against electric repulsion to form complex periodic structures. As the simulation runs, the structure evolves depending on how deep you dig. We begin at the top of the crust. Here, the pressure is intense but low enough that protons and neutrons can still clump together into rough, isolated spheres. They resemble meatballs, or gnocchi, floating in a thin sauce of free neutrons. But as you dig deeper, gravity crushes these spheres closer together. To avoid the massive electric repulsion of touching, they are forced to change shape. They merge and lengthen, stretching out into long, cylindrical rods of nuclear matter. The gnocchi has transformed into spaghetti. Deeper still, the pressure becomes unimaginable. The rods are crushed flat, fusing sideways to form continuous, solid sheets of matter stacked on top of each other. We call this phase lasagna. At this depth, the concept of an atom is gone. You now have single, unbroken planes of nuclear matter extending for miles. Then we cross a critical threshold. The universe flips. Suddenly, there is more matter than empty space. The lasagna sheets merge into a solid block, leaving behind only long, winding tunnels of void running through the dense material. This is anti-spaghetti. Finally, just before we hit the absolute center, those tunnels are pinched off. They become isolated spherical bubbles of void trapped inside the solid nuclear matter. We call this the anti-gnocchi, or Swiss cheese phase. Go any deeper, and even those bubbles are crushed out of existence. The pasta is fully cooked. You reach the core, a completely uniform ocean of nuclear fluid. But if we go back up to that lasagna layer, the structure is doing something incredible. Because of those continuous sheets of matter, breaking this material is nearly impossible. In a diamond, you only have to break chemical bonds. But here, to crack a sheet of nuclear pasta, you have to snap the strong nuclear force itself. According to our simulations, this makes it the strongest material in the known universe, 10 billion times stronger than steel. In fact, it is so strong that it can support mountains on its surface. Mountains that are only a few centimeters tall, but weigh as much as the Earth. And we know this because sometimes the crust cracks. When this material finally snaps, it releases a starquake, a release of energy so violent we can detect the flash of X-rays halfway across the galaxy. It is the universe showing us that while we can't visit and we can't touch it, the pasta is real.